So I think what we're working on is small oscillations. And I did the cycloid, right? Is that the last thing in our notes? Cycloid? You say Sam, cycloid? Not seeing there. And that was even homework. Is that homework? Oh yeah, so this was a homework problem, right? Yeah. So that was the last thing, right? The homework problem for the cycloid, small oscillations. Were there any other homeworks for this week?
Yeah. Also assigned a few problems about the Lagrangians and mass distributions.
Oh, okay, those would be good too. Yeah. Cyclic coordinates and that kind of thing. Good. So we have a couple things to look forward to. But now we're talking about small oscillations in the Lagrangian formalism. I'll remind us what we had so far, because then we're going to have to do a section on multivariable Taylor expansions. But we have a Lagrangian of this form. Minus u of q. And I'll even put the example there with your help. So this inverted cycloid with gravity there, minus 2r, 2 pi r. And we have its shape in parametric form. And you guys help me if I get this wrong, but we would have had m r squared, 2m r squared 1 minus cos theta, theta dot squared minus mg r cos theta. Is that what we had there the other day? But I pulled an R out. I pulled another R out there. Oh, gotcha. MGR cos theta.
Parentheses, r cosine theta minus r and parentheses.
Yeah, we could leave it this way too, because that would just be an added another arbitrary constant, right? We can take or leave arbitrary constants. So we can work with this one as well. Yeah, so anyway, this has that form. I think if we did the, let's go ahead and do it this other way. MGR. So then it would have been cos theta minus 1, right? We'll leave it like this. So that's sufficiently general. And what we found though, in order to find the small oscillations of this system, actually if you take the Euler-Lagrange equation of this, it's already going to be a mess. There's going to be a lot of chain rule and stuff coming through there when you take the complete time derivative. I'll put that as a note. If we do d over dt, dl d theta dot minus dl d theta equals 0, that's the Euler-Lagrange equation. You're going to generate a lot of stuff because you've got this a of q here. So I'll write this, it's complicated. So what we do is we produce the small oscillations, Lagrangian, and that is 1/2 a of q naught equilibrium point. So I did this last time. So we took the local equilibrium point, Q naught, and then we said x equals Q minus Q naught is small. And then we said A of Q naught has to be much greater than A prime of Q naught times Q minus Q naught. I'll put magnitudes around there. And we let K equal U double prime of Q naught. So that's a simplification. If you have a local equilibrium, local minimum of the equals local min of U of Q. So this brings us to here, and if we go through these steps, we can just read off the frequency. In fact, does everybody recognize this as the basic harmonic oscillator? Remember, the energy of the harmonic oscillator would be half mx dot squared plus half kx. And immediately you know what the frequency is. But we're going to do this anyway, okay? So d over dt dl small oscillations dxi dot minus dl small oscillations dxi equals, well, derivative with respect to x dot is mx dot, so mx double dot, that's our time derivative, and this other one here minus negative is plus kx equals 0. And this one you guys are supposed to recognize now, right? Harmonic oscillator equals minus k over mx, and then omega squared equals k over m. So that's one of the benefits of studying these things for so long. You just start to recognize something, and you can immediately cut to the answer because it has a generic form. So this was for 1 degree of freedom, and it did bring something new into the mix because this may very well be the standard kinetic minus potential for harmonic oscillator. But we achieved that in a slightly more general type of Lagrangian, right? Because when you had a parametrization of a curve, then you got this A of Q in the mix as well. Right? This thing here. So this was a little more general. Right, we had that thing in there. And it turns out that the minimum is going to be at pi. So cosine of pi is negative 1. You can have 1 plus 1. You're going to get an answer that you could not have guessed. Okay. Whereas if instead of a cycloid you had a semicircle, then you could have guessed the answer. Because it would be the standard thing. Okay. So yeah, this one you're going to enjoy. Just take it and just go through from the top. In fact, not a bad idea to review the derivation of the cycloid just so you have it in your repertoire. Okay, so next we want to do systems with many degrees of freedom. And I was going to bring some models to class, but I'll bring it next time. I was going to bring that double pendulum to class with the spring connector, but we've all seen that, right? Yeah. I'll bring it next time. So when we have many degrees of freedom, we have to do a bit more. Get some interesting results out. But first we're going to review, let's see what order we do this in. The multivariable Taylor expansion. We gotta review that at some point here. So springs. This one we're really going to study. It has everything. So what we do is we call this the x-axis. We say these equal masses, equal springs on the outside and a different one in between. In this system, one thing we'll prove is the small oscillations of the double pendulum are equivalent. So if we can hang a pendulum system like this, connect the little spring there, then the small oscillations of this system are equivalent to that system. We're going to prove that because then if you solve this one, then you just inherit this one. So that's an important point. If we have that model of this downstairs, I'll bring it back in. What we do here is we say the equilibrium point is when all the springs are relaxed on this one here. And of course, the equilibrium point here when they're hanging straight down and the springs are relaxed as well. But when they're not hanging straight down, then there's an angle theta 1 to theta 2. And of course, we have to talk about this double pendulum because its solutions are so amazing. So a double pendulum like this has two different lengths, two different masses, two angles. And I'll put that fourth one in here that's already been on our homework. So we have this one with the mass with a pendulum attached to it. Okay, we have that one as well. So this is a good collection. If we can work with all four of these, we'll be in good shape. These all happen to have 2 degrees of freedom. Anything more than 2 is pretty iffy as far as being able to solve it or not. So let's see. Okay, this one was a homework. And so we can continue working with this one. This one's going to be a homework. In fact, all of these we work on. Something together so we can all. So the question is, how do we find the frequencies of oscillations in a system in general like this? So we could actually title it small oscillations of systems with many degrees of freedom. There we go. Okay, here's how we're going to start. We're going to start with the more general Lagrangian. So we'll look at systems of this form. L. And we've built these up, right? AIJ, IJ, Q, UJ. That's kind of our most general Q1, Q2. We really want to do exactly the same thing we did for the 1 degree of freedom, right? You notice that these go from 1 to n. And if n is equal to 1, that's the one we just did a minute ago. So what we have here is equilibrium at Q naught. So just to visualize that, suppose I've got the whole vector Q here, then I've got a Q naught, and I've got a local bit. So same as before, except now we need to know about local minima and functions of any variables. We need to know functions of any variables. In particular, we need to know their Taylor expansion. So I did that in math methods, but I'm going to do it here as well. Because experience shows that people don't know the Taylor expansion as well as they should. So we'll just review the multivariable Taylor expansion, and then we'll return to this thing. And this derivation of the multivariable expansion is interesting in its own right. So what we want to do is expand some function f of x. X has n variables in a Taylor series. And this time, we just go to second order. And we're going to expand a Taylor series about some x0. So yeah, in 3 dimensions, we could say I have a temperature field in this room, and we'd have some point we expand around to some scalar. But there's an interesting construction here. What we do is consider this. Consider f of x equals f of x naught plus x minus x naught. So this is the quantity that we're going to think of as being relatively small. Notice x naught, x minus x naught. So we're expanding it around here. It's kind of the way you do when you say f of x plus h or something, right? So we consider this, then we're going to let g of t equal f of x naught. Oops, it's f of x naught plus t is a vector x minus x naught. And t is just a real number. So what is this geometrically now? Geometrically, I'm out here in space. So here's x naught. This is x. This is x minus x naught. Right? Little vectors, arrows. And t times x minus x naught would just encompass all the points along this line. So the strategy here is to expand g in a Taylor series. We'll have g of t equals g of 0 plus g prime of 0 t is a t plus g double prime of 0 1 half t squared. And then g of t equals 1. G of t equals 1 is going to be equal to f of to get a little practice with the chain rule. So, because what I'm doing here, so this thing right here, this thing star, that's the expansion along the blue line. Expansion along the blue line. So let's, so we have free G of 0 equals f of x. Now we have to do G prime T. G prime of T equals d over dt. So we're going to write this thing out as follows. F of x not 1 plus t x 1 minus x 0 1 comma x 0 2. Sometimes you gotta have all these arguments by the end. X 2 minus x 0 2 plus all the way down to n. When you take this derivative, what you have is this is a big chain rule. Remember n variables, so you have sum over df, I'm just going to write dx of I. I'm just going to write those arguments in there, of the arguments, and the chain rule gives you that derivative with respect to t. And the derivative with respect to t is just always xi minus x0i each time, right? Don't worry about this. Then when we evaluate at t equals 0, then boom, we're just evaluating at x is 0. But for the moment, we'll leave that there. And and this is actually almost the final form here. G double prime, this one's even more fun. Okay. So what we imagine is this is just a function of these arguments again. Thing in the parentheses. So we need a new sum. We'll do j equals 1 to n of the derivative of this thing the same way we did it here. So what we're ending up with is a second derivative. So we have e squared f dxj dxi. We've already got the xi minus x0i, and then since we're doing it with respect to the j's, it's the same thing. The t picks the inner derivative, just picks off the thing that's proportional to t here. So we have xj minus x 0j. That's the second derivative. Now suppose we wanted the third derivative. At this point you can actually see what would happen. Anybody?
We have another summation.
We'd have another summation, and then what?
Dxi, dxj, dxk.
So d cubed,
I think so.
xi, xj, xk, and then we pick off an xk minus x0k.
Yeah.
So this is perfect for a machine to do, but we're going to stop at the second derivative, because that's all we need. In fact, if you need higher derivatives in physics, you'll usually go to different coordinate systems. This is for Cartesian coordinate systems. But yeah, you see the pattern, right? And now we just have to go back to here and evaluate it at t equals 1, and we'll just pick off this, the linear, and then 1/2 times the quadratic term. So I'll just put here as a note the third derivative, t, would be k, j, I, I'll just write et cetera. We just saw it here, don't get it right now. We just saw it sort of on there. But now we're going to pull it all together. And I just want to impress on you guys that this is just bookkeeping. And otherwise very intuitive. Let's have a look here. So for t equals 1, we find the following. F of x equals f of x 0. Point where e f x I of x 0 x I minus x 0 I. So I equals 1 to n. 1/2 double sum ij x I dxj at x 0. And then we have to write in this xi minus x0 I, xj minus x0 j. So when you're confronted with this kind of complicated looking bookkeeping, it's really important to recognize what you have for the n equals 1 case. For n equals 1, we just have f of x equals f of x 0 plus f prime of x 0 x minus x 0 f double prime x minus x 0 squared. Right? You're just back to your standard Taylor expansion up to quadratic order. And this you should feel really at home with at some point, especially when we introduce this, when we talk about it, we know, for example, that there's our linear approximation of our straight line formula, or a point slope. So if I just had some nice curve here, and let's just for the sake of argument put the x0 right here, then f of x0 would have been that, and f prime x0, x minus x0 would have been this straight line, and adding the second derivative term would have put in a little curvature here, say, right? So this is the one you want to have in your mind's eye always, even when you're looking at this complicated thing. And what you see here is another way to look at this is gradient f dotted into x minus x0. Right? Where have you seen that before? That's pretty standard in 3 dimensions. Right? This here, though, this is the matrix of second derivative, the square matrix of mixed partials. And it even can be written as a vector, matrix times a vector times a vector. So yeah, you just want to be comfortable with these things. So now that we've gotten this far, what's the criterion for, say, a local minimum or local maximum? In 1 dimension, very clear. This guy has to vanish, and if it's a local min, this has to be positive, local max has to be negative, right? Or else it's the saddle. So what about in this more general world? All of these have to vanish. We actually used that already when we talked about the variation calculus. So for a local min or max critical point, all of these partials have to vanish in the gradient. And then this matrix here has to have certain properties. If we want to have a local minimum, this matrix has to be be what's called positive definite. Local max, it has to be negative definite. Okay. So that's where we are right now. And we're going to go back to our potential energies and just change the letters and then talk about this stuff. So I'll put those properties up here. And always remember, this is one variable version. This is the one you actually know and understand. And then you understand these more complicated ones in terms of the basic one. So let's have a look here. I'll put these conditions. So critical points. N equals 1, f prime of x0 equals 0. Good. And for a local mid, f double prime of x0 is positive. Okay. That's the way we learned calculus the first time around. For n greater than 1, we have df dxi of x0 equals 0 for all I and n. And so this was this here. Okay. Then we need d squared f dxi dxj x0 is a positive definite matrix. That's called the Hessian matrix sometimes. Anybody ever had that nomenclature, the Hessian matrix? Now the nice thing is that in physics, we generally don't have to verify positive definiteness because we start with something that was positive definite. Let me get a criteria here. I'll just do this right here. So this matrix of mixed partials. So d squared f dxi dxj of x0. I'm just going to call it aij, okay? And if you have, if aij is this matrix here, a11, a12, a1n, an1, ann. Let's get this guy here. The criterion for positive definite is that if every one of these corner determinants all the way down to the last is positive. So if determinant A1 to A1K, AK1, AKK is greater than 0, strictly greater than 0 for K equals 1 to N. All of these corners, so whatever, you have your determinant, you have your matrix, and this upper left corner would have to be positive, and then the 2 by 2 determinant would have to be positive. So suffice to say, we generally don't have to do that, but you can look this up in the linear algebra program. yeah, what we need is this positive definite right here, and that means it, and that is the second derivative criterion for something being a local matrix, so something always being positive. So yeah, just have that in your notes for the nomenclature, Hessian matrix, all these order determinants we enter into it. Hessian matrix. Here. The Hessian matrix is positive definite when all of this is true. There we go. That's not right. So what I can do now is write down the whole Lagrangian small oscillation Lagrangian pretty quickly, and then won't be much more today. But make sure you have all these there. We're going to practice these second derivatives and stuff, these expansions. Yeah, so this complicated one, you guys refer back to the one variable. That's the tip for understanding it. And I'll go ahead and erase this over here. So now we're returning to that Lagrangian 1/2 double sum, etc. Okay, we're returning to that thing, and I'm just going to construct the small oscillations Lagrangian, and we'll justify it by. So from L equals 1/2 double sum ij. It's a very general form. J dot minus U of Q1 to Qn. So back to this thing. We obtain small oscillations from Jim Bell's small oscillations. And myself in the room. I'm just going to write it down and then we'll justify it step by step. So what we end up with is something that looks like this. Mij, I have a matrix xi dot xj dot minus 1/2 double sum ij kij xi xj. Imagine n equals 1, you're back to the very trivial simple one. So it's all in the definitions here with this Mij equals Aij of Q naught. So we have an equilibrium point. Actually, let's add this with equilibrium at Q naught. Q0. There we go. So we get the small oscillations form. We have the x of I is the small quantity Qi minus Q0i. And what's missing here? The Kij and Kij equals the second derivative. Qi, Qj. And Q0. I really like this form. Line evolutions do this because it looks just like point metric things, right? So these are now matrices, and I'll put an important note here. This Mij equals Mji. So the symmetry of that matrix is always possible. Using the proofs, same thing here. Kij equals Kji. If it isn't when you're constructing it, you just make it so. So let's add a problem to the gonna do the two pendula connected by a spring. Okay. Two pendula here. We're gonna have pendulum, pendulum. Put a spring right there. Theta 1, theta 2. And the equilibrium with the relaxed spring is going to be at theta 1, and theta 2 equals 0. So equilibrium when theta 1 equals theta 2 equals 0, and the spring is relaxed. So what we want to do is just construct the Lagrangian. And I have to give you an important tip here. Construct L and 2, construct small oscillations Lagrangian for this one. Now an important tip is this. The energy in that spring can be very difficult to construct if you have arbitrary angles and you have the Pythagorean theorem. So construct L, I'm going to write here for the spring. Use potential energy of the spring equals 1/2 K L squared theta 1 minus theta 2 squared. So we'll ignore the Pythagorean theorem aspect of it. Okay. That'll just keep things simple. And when we work on that together, we can explore the other part. But yeah, if you take angles where these things are really, out like this, then you're not going to be happy. So you take a little over. So this itself is already pretty small oscillations style, and it's saying that the angles are fairly small. But otherwise, we want to, have it in terms of the cosines of these. So yeah, of course we've got gravity pointing down there. So we'll do L, then we'll do L small oscillations, and we'll try to put it into this standard form, which I'll talk about more later. But this gives us a good collection of things to work on. Wednesday I'll talk about the double pendulum as well. That was a mess, right? But now we have a nice collection of things going on. And I'll try to remember to bring this thing to class and we can talk about it a bit as well. Good. So yeah, we got a good collection. This week, Friday, we're definitely gonna spend an hour working something forward. That'll be more fun. Okay, good. That's all I've got for you.